Thank you for being part of lecture number 20 by Dr. Emanuel, Cylindrical Coordinates. We've been talking about a lot of rectangular coordinates, so now we're going to be talking about some polar coordinates, which is very important in different applications that you'll be working and using over history. So, what do we have here? Let's simplify integrals containing circular symmetry. Okay, we have the symmetry here. And so what do we have here? We have y2 a squared minus x squared, square root of it. And then we're going to have also y1. And with y1, that will equal a minus the square root of a squared minus x squared. As you can see, your a's are controlling your x's here. And it'll be symmetrical, so these would be a also. Okay, so if we want to find the area, what do we need to do? Okay, if we're going to do dy first, then we have our what? y2 and our y1. Plug them in, and we know it goes, since it's symmetry, from a minus a to a plus a. Minus a to plus a. We take the integral, and it's just y, and all we do is put in a squared minus x squared, the square root of that. Then you're taking the minus of that minus the lower limit. It gives you 2. Okay, let's see how complicated this is for solving and how we can simplify it, because that's what we want to do. We want simplification when we deal with all of these circular symmetry. Okay, as you know, that a squared equals what? X squared plus y squared. We're going to be using that formula as we go through. Okay, so as we use polar coordinates, as we simplify the integral containing circular symmetry, we have here some formulas we need to remember. X equals the cosine of theta times r. And then y equals the sine of theta, okay, the sine of theta times r. So one is opposite, which is x, and opposite, which is y, and adjacent, which is x, for theta. And what we want to do is differentiate. And so we want to find out what the smallest change we can make on theta is called d theta. And for r, the small r, it's called what? dr. And we have here in the red r plus dr times d theta. As you can see here, we're going to be using r dr. We have x equals, we have the x and the y, we mentioned those already, the sine and the cosine. R squared is equal to x squared plus y squared. That's vitally important for small. Then we have x squared plus y squared equals a squared. And a squared is what we were using right here, since it's symmetrical. We also have the tangent. We have what? Y, which is sine over cosine, which gives us tangent. Remember, from complex numbers, the point R is also equal to R and the angle theta. This is for small, now for small angles, d of theta with dr. It is, now the area is r dr. This is r. Then we're going to add that little difference. Okay? And d theta, which is the change in theta. This is theta, and this is the change in theta. When we talk about the change of the area, the differentiation of the area, we have dx dy, and that is now in polar coordinates going to be r dr d theta. And it goes along with the what? Area. As you can see, the differentiation of the area. Much easier integrals contain circular symmetry. You're looking at the same example. And as we plug in the new values, we have r dr d theta. And if we look at this, as we look at this here, we can see that we go from 0 to a, our radius, 0 to r, and we go fully around from 0 to 2 pi. Take the integral of r dr, we get 1/2 r squared from 0 to a, and that'll be 1/2 0 to a squared, and this just goes to, this is for theta, it's just going to go to 2 pi. 0 cancels out. So with the 2 pi, it's 2 pi. And then if we cancel out the 2's, we get pi a squared. Okay, so let's look at an example. Find the mass of a circular disk of radius 3 with density equal to x squared, where x equals r cosine of theta. Then plugging this value in r cosine theta into this formula for density of x squared, we get it equal to r squared cosine squared theta. So the mass formula is triple integral of the rho dv. So this is our rho. We have that here, and this is our dv. And we go from 0 to 3. As you said, our radius will be 3. Our radius, and we're doing what? 360 degrees, which is 2 pi. So let's try to integrate and look at this, or at least group terms at this point. So here we have r and r squared, so that'll give us an r cubed, our dr, and we have the cosine of d theta, cosine squared. Cosine squared of d theta from 0 to 2 is equal to pi. And if we integrate r cubed, we get 1/4 of r cubed, r to the 4th. And we're evaluating it from 0 to 3, and we get pi. The constant comes out. We have 3 to the 4th pi was 81/4. Okay, we've done a problem and we've gone through the basics. So we like for you to practice using a practice problem. So this will be end of part 1. We'll come back and deal with some more examples so that we might be able to make sure we understand what's going on. Thank you once again.